Good evening and welcome to our first Sunday of the month live broadcast. Once again at our host Rob's place. And at the moment we have Shannon with us. We're going to have a couple more join us for our Electric Cosmology Talking Opportunity. Tonight we're going to be talking about very small things, and our special guest is none other than Edwin Kaal, who is joining us tonight from the Netherlands. Do you want to say hello, Edwin?
Hello there, everyone.
Hi. Thanks for coming. And yes, so basically we're going to be exploring the world of the very small. And we're going to be looking at different models. I mean, we are going to look at primarily what Edwin is coming up with, and even a variation of by myself. But there are other models as well. So, Edwin, do you want to start and actually explain the conventional model, like the Bohr's model, and even sort of like electron shells? If you can explain, then we'll go on to the alternative models, including yourself. So can you explain sort of like the first sort of, original models?
It's quite a challenge because there are, of course, many models out there, but to give everybody an idea of what we're talking about, conventionally, the atom is seen as a nucleus with outer electrons, right? And the nucleus conventionally is made up of protons and neutrons. And exactly how they are structured together is one of the mysteries that we're hopefully touching upon tonight. But conventionally, it's often compared to a solar system model, which is not accurate because they are not, the electrons are not orbiting in a planet-like fashion, if you will. You mentioned the electron orbitals, so you could equate them more like magnetic fields or something to that effect. And with certain angles and sizes, if you will. So that is how we conventionally look at the atom, in a nutshell.
Okay. Two of the problems that occurred to me with that model when I was at school, is why don't electrons collapse into the nucleus through attraction, and why doesn't the nucleus blow apart because like forces repel? As a starting point, it was even 17 years of age. It seemed a little incomplete. Is this where the Bohr shells come in? Do they somehow mitigate that problem?
Well, you see, I think your questions, first of all, are very good questions. I've had those questions myself for many, many, many years as well. And it's not that I can totally answer it to complete satisfaction. What we can say is that conventionally, you pointed to the nucleus is staying together instead of exploding because they're all positive particles. The neutrons that are there are allegedly neutral. So meaning you would be left with nothing but positive particles, and they should make distance very, very rapidly with a huge explosion. The fact that it does not do that led to whereby the postulation was, well, then there must be another force, a really, really strong force, hence the strong force, the strong nuclear force, and that to that assumption, if you will, and that was the answer for the fact that it would stick together. The other thing that you pointed out is, why do electrons not fall into a proton nucleus and annihilate each other, for example? I cannot give you the definite answer there, but I would argue that the proton and the electron quite differently from the current mainstream version, if you will.
So how do we? I mean, we can't see an atom. We can't see the nucleus and electrons whizzing around in whichever form they may be. So how do we actually tell what they look like or what they are? I mean, what do we get? Computers spitting numbers out, or how does it work?
Well, for start, again, I believe nobody knows what a proton exactly is or what an electron exactly is. What I can do is speak from the structured atom model. That's my cup of tea, if you will. And what I've been working
But how do they originally come to their ideas? I mean, how do we measure these things? Is it literally computer numbers? I mean...
No, I think it started with, a good example would be to look into Dalton.
Okay.
Dalton was the one that noticed ratio numbers. So this is very important, ratios between the element weight numbers in chemical reactions.
Right.
So just an example from the top of my mind, everybody knows CO2, right? So 1 carbon and 2 oxygens. So there's a ratio there of 1 to 2. You need 1 carbon for every 2, or 2 oxygens for every carbon.
Okay.
So that was the start of it. And you can also continue then by measuring the weight of certain elements, and then you start figuring out, hang on, they have different weight numbers.
Oh, okay.
And that's what led to the numbering of the number of nucleons, so the protons and neutrons conventionally.
Yeah.
So that number was, every atom or element that we find.
Unfortunately, we got
like a mass number, if you will.
No, unfortunately, we're getting a bad connection though, just coming up. Can I call you back? Should we break this line and we'll call you straight back?
Yeah, sure, we can do that.
I think that'd be a good idea. Hold on.
Yeah, because we're getting negative responses on the live feed.
Yeah.
People send the videos down. They can hear, but they can't see.
Did you shut the Facebook feed down?
No, I think so, because I've seen it.
Have you shut all your bits and pieces off?
I think it's okay. People are just moaning that they can't see.
Yeah, okay. Oh, go away.
More.
No, good.
Just chocolate peanuts. Peanuts and raisins, Bill.
Sorry about this, people. Go away.
Top left. Top.
Sorry, people. Let's just try and get him back, see if we can get to a better idea on the man.
That couldn't call him back.
Hello, you're back.
Good.
Okay, okay. We'll see if we can get a better line. But it seems like the internet line into the property is slow because we're getting break up on Facebook as well. So we will soldier on and we'll do the best we can. Anyway, you were saying, sorry about that before we was interrupted.
So nucleon weight. Nucleon mass, sorry.
Yeah, so it's at a certain point, and I'm not sure when and where exactly, but some names come up. Dalton I mentioned already, and he makes the connection to atomic weight and ratios, etc. So we started to understand that there's a particular number of nucleons, right, for every element, if you will, and that was, in my mind at least, the start of the building of the periodic table of the elements.
Okay.
Then you get a Mendeleev, for example, who of course famously put it into the current, more or less the current periodic tables layout, if you will.
Yeah.
And from that moment on, it's a little discovery here, a little bit bigger discovery there, right? The discovery of the fact that there are things that we can call protons or neutrons.
Right.
There are things we can call electrons, and from that moment on, we end up, and then in the end we end up where we are, of course, right?
Yeah.
Can I ask about Dalton, because I know he was an advocate of a solid particle, and in a discussion we had in November, it came out that Michael Faraday, for example, didn't really subscribe to Dalton's model and was more keen on the Boscovich way of looking at things. The point that precludes any other point coming into it, but it doesn't have isn't actually a solid point in the middle. Boscovich is more energy. I know when you spoke to Neil Thompson, there was talk of the Boscovich model, but I wonder if you could, for me, just clarify why it seems to me that you prefer the Dalton conception of a solid particle rather than the Bos. That might be an oversimplification. I'm sure it is, but I just wonder how you came to the conclusion you came to between those two very broad models.
Well, first of all, I have to say that the structured atom model is not based on any other model or concept.
Okay.
Right? So I've taken the liberty, if you will, of do some creative thinking there. and following my nose wherever the evidence and the facts and observations would lead me.
Right.
So to start out with, the fact is the structured atom model, basically the only particle but we recognize, and it's literally in that sense of the word, it's a part of a bigger whole without knowing what it exactly is, right? I'll be the first to admit that.
Okay.
But it's a particle, and a particle in a three-dimensional world we would see as a sphere.
Yeah.
That would be the most logical thing to conclude. The electron I do not see as a particle at all. I see it more like a concentration of charge. Now, how that exactly translates into the current physics is a whole different ballgame.
Yeah.
That's something that we are currently trying to dive into very much in connection with other physicists and electric engineers and some other people to figure out how that exactly works. So what I'm trying to say here, this is a concept, right? I'm not saying this is like...
You've got a description, not a definition.
Yes, so this is described for your understanding, right?
Thank you.
I see a proton as a charge carrier, the electron as the charge that accompanies that proton, so they are equal yet opposite, and that is how a nucleus in essence would stick together. However, we know there's this thing we call electromagnetism, and right now the debate that we are having, and there are scientific papers that are being written, not yet published, that dive into an electromagnetic nucleus, if you will. So meaning we have an electromagnetic nucleus built up from these protons and the electrons that I just described, and that away in a specific structure is what determines the specific elements in the isotope. So
you say some papers being written, and they've been written at the moment?
Yes.
When do they hope to be published?
Well, I can only speak to what I know, and there are a gazillion of them out there, but we have like 1 million papers per year that are produced or something to that effect.
I hate to correct your English, Edo. I hate to correct your English, but gazillion isn't a real number. Sorry, that was going to be a joke.
Say again?
So I hate to correct your English, but gazillion isn't a real number. No. Sorry, that was a joke. That was meant to be I apologise.
No, it's okay. I'm a student of English, it is not my first language.
I'm sorry. I'm sorry, it was a bad joke, I apologise.
Right, very English.
So that's how we arrive to the concept that we're dealing with the structured atom model. And yes, there are papers that are being written. The ones that I know of are not yet published, but I think this year for sure somewhere they will be published. But they dive into basically, and this is not my cup of tea, mind you, I'm not an electrical engineer, so when I say something stupid on that field, please forgive me, but it dives into the Maxwell equations.
Okay.
And from these Maxwell equations, now these people do something with it, but they look at the nucleus, so these are physicists with mathematical capabilities, and they're looking at the nucleus in an electromagnetic way with Maxwell equations, etc.
Okay.
And it's based on the concept that I've been proposing as well, like, and I'll do it visually, a proton, another proton, and an electron in between.
Yeah.
Now exactly what happens there in more quantum mechanic and physical terms, I will leave that up to those people. When those papers are published, I'll be the first to share them, of course, right?
So do they include the neutrino? Because obviously in my sort of like way of thinking, yeah, and the ether, the electromagnetic ether, how does that interact with your model or how the papers they're writing? Does it at all, or does it not even have any interaction with the neutrino? They're just passing through without any way of actually them interacting with matter?
Now, I'm not saying the neutrino or the phenomenon neutrino is not important, but for this particular debate, if you will, it's not a primary thing. At least it didn't pop up yet as being super relevant in that sense.
Okay.
So the thing that I'm always after is, how are things structured? So a simple question would be, what makes oxygen oxygen? And what makes an iron?
Yeah.
And so these are the questions that I've always had in mind to satisfy my curiosity. That's what led me on this path, and in the end, in this whole model, if you will.
Yeah.
So you can look at that model and now go like, okay, that is why oxygen is oxygen, and that is why an iron is an iron.
But you don't have any problem with my adjustment. The fact is, we only have neutrons, and it's the interaction with the ether come neutrino that makes it appear to be a proton, and in that you get the energy release, which is the electron, which is a byproduct of it becoming a proton. Because I see this in because you work very much from the single hydrogen, and that single electron, and my stuff in weather forecasting is, the actual layer that touches the surface of the Earth is very important. That's where clouds don't go. Yeah, fog is, but clouds won't, because it's negative against negative. And so I can see with two protons, and they both create a negative shell, and that is what keeps it at a distance. You see what I mean?
That would be the case with two hydrogens, yes.
I mean, because I don't know how that works. Because it's also going onto molecules. Because obviously, we're getting so you're breaking up.
Know how this works. Otherwise, it would be out there right now being celebrated, right?
Because I also saw his interest with the probe in Sapphire, because it went in, but it soon again touched that in the inner layer, which touched the anode, that surface layer, it vaporized. And so this is what I'm seeing. Yeah, so I'm wondering, whether this is the tie-ups and going into molecules. Do you think the molecular bonds are little Birkeland currents, which are holding an exchanging charge, which holds it together? Is that?
It's again a very good question. I cannot say. I do not know.
No, I'm just chucking ideas out there.
It's one of the points that have been raised in this whole network of people that are talking about these topics, right?
Yeah.
What is a chemical bond? Even in chemistry, we say it's the sharing of an electron, right?
Well, yeah.
And you can look at it in an electrostatical way, if you will. That's one way of looking at it. But is an electron shell, is that actually, as you suggested, something to the effect of a Birkeland current? Could be. I don't know. I cannot zoom in on that level, right? That may be something for in the future that we can determine.
Yeah.
I just think that we need to look at the structure of the elements first before we go any further. Otherwise, we will not truly understand what is happening there. The structure dictates the properties of the elements. That is an important thing to understand, meaning the nucleus, through its structure, dictates the structure of the outer electron orbitals.
Yeah.
That dictates the chemical bondings and the angles of bondings, and that, of course, is important in our lives, in chemistry, physics, but also in structural things.
Okay. Well, I think we should backtrack, because we talked about different models. Now, when we talked about this Boltzmann model, and I know a lot of people in the electric universe like it, so I'd like Rob to basically...
Well,
Is that possible? Can you?
I don't know what you're asking.
The Boscovich model. Can you describe how it works?
Well,
I can look at a little look at it, didn't you?
Yeah, I mean, and I know, Edo, that with Neil Thompson, Electric View, this was a subject for discussion, but my understanding is the Boscovich model, there isn't a solid centre to the particle. It's a sphere of influence is the way he put it. It's a field. As you get closer to the centre, let's say the centre's here, you get areas of attraction, areas of repulsion. That and as you get closer and closer to the centre, you get almost infinite repulsion. So you get these. Hang on, I think Edo's got a picture.
He's getting a book. That's for certain.
Oh.
Yeah.
Yeah. Haven't read it yet. Got it on order. Yeah, that's yeah. Thank you. Yeah. So you get these areas of attraction and repulsion as you get in closer, the distance between two particles, and you get these natural points where you get, if you like, valleys and cliffs, and the distance between two particles tends to fall into one of those valleys. And if you're, if you're on a hilltop, one side, the particle will either get closer or further away. It is similar to, it also appears.
But
it also appears to work in a scalar way.
Okay.
Which is why some people say that, for example, it explains the stability of planetary orbits. If they get too far away or too close, they'll get bounced back by the shape of the attraction and repulsion. As I recall it, attraction is the inverse square, an inverse square law, and repulsion is inverse cubed. Now that's what I've heard. I've still yet to tease out how that relationship becomes, or how he derived that particular wave, but it is something, for example, Roger Anderson points out, occurs on lots of different scales. So it's an interesting model, and seemingly a very intuitive one, because Boscovich was a Jesuit priest. He studied maths.
Oh, okay.
He was obviously quite bright because he was one of the Jesuit priests that went off to Rome and got taught there. He became a professor of mathematics there. He was obviously a great theoretician and a great thinker. I'm not at all clear that he ever got his hands dirty in a Michael Faraday.
No, he was a mathematician. He wasn't a scientist.
Yeah. So again,
controversial.
Well, not here. But
No,
that's a brief overview of the Boscovich. Boscovich atom.
Okay.
Again, not a solid core, but a field of force that becomes stronger and stronger and stronger. So when you basically got an exclusion principle, because you can't have.
So it's purely filled. It's not
purely filled. And it's what the way I became familiar with it, or initially, was through Michael Faraday, who was very much anti-Newtonian, which is again something you could get into, but he favoured the Boscovich model over the Newtonian particle.
Yeah. But you and Blau and I prefer the particle model. Yeah, definitely.
Well, I would argue that that's usually
line goes down
with this model, because, as I explained, see the proton as a classical ball, a sphere, particle, if you will, solid thing, and I see the electron causing this.
So it's the electron that's causing that.
I think it's the fields, the charges, the potential wells, all these things are in the realm of electromagnetism.
Yeah, absolutely.
And I believe that it is the charge, the electron, that is accompanying the proton. It is that thing or that combination that will create these double layers. That will create this wave function from Boscovich, that will create the shells in a sapphire experiment, or the double layer effects that we see on the Earth, because 100 kilometers up the atmosphere changes drastically more into an ionosphere. But 30 kilometers down beneath our feet, we see, and this is a difficult name for me, Bohorovich barrier. It's a very relatively thin barrier where the speed or the sound wave suddenly very much changes, so we think it's like a magma layer. So we see these double layers everywhere, and I believe it's caused by the charge, so that's an electromagnetic thing, if you will. And, I believe that is surrounding the proton, if you will. So it's like the combination of the two that creates these things. So exactly how is the question before?
Yeah, no, I still go back to the ether and the interaction of that, and well, whether it's how, but yeah, the electron is very much an energy response. I see, being created. Because I think about that, because they talk about moving electric current and it's electrons moving. Well, are they, or is it just the ether moving? And so creating a moving electron. It is certainly one. Yeah, I'd like to explore, but it's not my field. It's not my field, and I can only sort of like go so far. But it'd be interesting. I'm sure we will, with the good work itself. I mean, once you actually go into your website and you actually look through it and how it works, and geometric form is throughout nature, what we can see up to galaxies. You can see hexagons in galaxies as well as a snowflake. I can't see anything else but the whole of reality being electrically driven. But yeah, is it coming from the ether, or is it separate to the ether? Or
well, the ether is a most difficult topic.
No one likes to handle it or look at it really.
Well, there are many goals and thoughts about the ether. You can see it as absolutely nothing, irrelevant. You can see it as a space-time continuum. You can even see it as, I'm not even sure what the terminology is there, like an electrostatic field that's perturbated with a light, which then doesn't even travel really.
Right.
So there are many ways of looking at it. I'm really, it's really for me, it's up in the air what it is, except it's space. That is an important thing. Space is connected to time, if you will. Changing relatively a position and distance and angle, etc., in relation to each other is what causes time, and time is energy. So what is it?
Is time consciousness? I mean, or is it? Do you obviously say more than just consciousness? You know.
That's a whole. What is consciousness? I think it's very important. Yet we shouldn't put that into the equation every time, right? Okay. But I consider this a very important.
I think this would be a good idea to go over to Sharon. And is there any questions coming or?
No, I've asked twice.
Oh really? Oh,
but you know that we're actually having trouble with the video. So some people have come on and then
disappeared.
Yeah.
Well, hopefully we've fixed that now. So if you'd like to sort of check on the groups to make sure it's coming through okay. Go for it.
So Ed, so I understand. Well, having had a lot of fun on your website, etherealmatters.org, and seen your talk at Bath as well as some other stuff, your conception of the nucleus as sort of constructed of Platonic forms. What does that give? Why is that a better description? What does that give us as a description of reality, as a description of the smallest part of reality, or one of? Why is that attractive to you? I'd love you to go philosophical about this, if you would. Like, go as broad as you can.
Repeat the question, please, in short. We have sometimes the poor network connection there. Please repeat it in short.
I'll try. Brevity isn't my thing. The structure of the nucleus is geometric Platonic forms. What advantage does describing the nucleus that way give us? How is that a better description?
Okay. So what we found was that the nucleus has, when you look at the first light element, this is the heat. Then you have lithium with a difficult word, pentagon pyramid, which is a pentagon with two polar spheres and 5 ring. And then when you reach the carbon, you have an icosahedron. Now, what the nucleus does is grow towards the icosahedron, which is represented by a carbon, and then it starts repeating that. What I mean by that is that it keeps creating that carbon shape, that icosahedron shape, made up of 12 spheres, in perfect geometry. So that is the Platonic solid. And the next group is like that as well, but there are 2 carbons that can to 1 carbon every time. That means you get a doubling fashion. So you 1 carbon, 3 in total, 2 carbons, and then 4 carbons, and then 8 carbons. So repetitive thing. So we can see the periodic table is made up of rows.
I was going to say this is kind of like the octets, yes, or what other people have called the octet. Sorry.
Right. So, well, that's leading automatically towards the answer, if you will, of the question you asked, because what you can see is by looking at by finding the structure, looking at the structure of the element, you can compare, and you can see what is actually happening there without using any formula yet, without using any mathematics yet. That means it's simple calculus, adding and deducting. That's not much. Counting, if you will, and then you can see that the structure determines actually the properties of the elements.
Right.
So a child can do the laundry, or if you can count to 10, you can call the whole world, right? It becomes very easy suddenly, and I would argue that the biggest benefit of this model, if you will, is that even children can understand physics to a high degree suddenly, because you can intuitively and structurally, visually, in a 3-dimensional shape, you can see, okay, what are the properties if I do this to the nucleus, what happens, but what will it decay fast, etc. Things are answered.
So are you thinking about, sorry.
Continue, please.
Well, are you thinking about producing some kind of teaching kit around the structured atom? Because you say it becomes not quite like Lego, but Lego-like, and you can start modeling, get students to physically model the nucleus and gain insight that way. Is that the kind of route you'd want to go down?
Yeah, possibility, definitely. You could Lego kits something.
Yeah.
What usually, and I'll try and show, what I usually point out, you can create the shapes.
Yeah, using neodymium.
Neodymium. I'm not sure how well it comes across.
No, it's looking good.
But what you're looking at here would be, in this particular case, an oxygen. So you can truly mimic, and the shape is also quite nice and sturdy.
Yeah.
It doesn't want to break readily once you have the correct structure, that is. So this offers a great tool for learning for children, especially. You can experience the forces and that there's forces at work there. And that's just a concept to put into your head. We tend to think, we just put a few particles together and we can do some calculus with it and it's all fine.
Yeah.
Forgetting that before you put 2 particles together, you may have experienced a huge repulsion force, or it starts to morph and meander.
Yeah.
So the thing you will find out when you work with the magnets and try to mimic the elements, that it is a self-organizing system essentially.
Yes.
Which must be true, of course, because the elements are always the same and constantly created.
Yes.
There must be an organizing system, and this is one of the things that you will find. Why this is an important or handy thing to do. the structure of the nucleus, that is, and the repeating form and shapes.
So, I mean, I know where Nobby's getting to, because obviously these next set of months are we're exploring how we're going to put a curriculum together for a summer school. And yeah, we're wondering, you know, whether you'd sort of in some way like to sort of be involved in that, where, you know, as far as the small scale goes. You quite fancy that?
Please repeat that.
We're putting a summer school together, so we was going to ask you to get involved possibly with looking at the very small as far as that part of the curriculum, because, you know, we're going to try and teach cosmology over the fractal sizes from the atom up to galaxies and beyond. So obviously, yeah, we're looking to put a curriculum together. So if you want to get involved in that, we can certainly, you know, talk this further in the future.
Yes, that definitely happens very much, because I believe it's important to reach, especially the younger ones amongst us, the children, if you will, the next generations, to give them these kinds of tools that would greatly simplify for them to reach a level, right, of understanding that you may be able to reach right now when you do a huge amount of study and papers and physics and whatnot when you're 50, and these children will be able to reach the same level at 17, 18, no problem.
I mean, what I liked about physics at school was we had lots of toys to play with, ripple tanks and lasers, and I won't go into it, but we had lots of toys. So very much the hands-on practical side is very important in learning. And you think, well, how do you do that with atoms, which you can't even see, let alone manipulate? But doing it with the ball bearings, your magnets, your round magnets, you know, it's these hands-on and people can play with it. It's a good tool, a good learning tool.
Yes, I would definitely be in.
Thank you.
Right. To work with that.
All right, we'll talk about that over the next few months.
Can I ask, again, thank you for being here. I've had a few questions ready. With the Sapphire project seemingly being able to transmute elements, how would you, in terms of the structured atom model, how would you model that? Sorry, I'm using the word model too many times, but how do you understand what's going on there, or what seems to be going on there?
Well, I can't speak for Sapphire.
No. Sorry,
but we can dive into the topic for sure. So I do not have enough information to give you a conclusive answer there. What exactly is happening on the field of transmutations? Of course, they express their interest very much in that field, looking at LENR, if you will, low energy nuclear reactions.
Yeah.
Is currently more or less the term that's being used internationally.
Can't use fusion anymore.
No, well, it is. Well, it depends on your definitions here.
Okay.
So fusion we consider more or less like helium or deuterium putting together into helium.
Yeah.
And transmutation would be more to the effect of turning a nickel into a copper.
Okay, more complex. Yeah. Okay.
So, but yeah, well, what's in the name, right? Well, some people would disagree with me here, but
sure.
So is it easier to transmute up or transmute down? To break stuff apart or add to it, or?
Yeah, you know, as we know, happening. So yeah, these things are definitely, we can describe those reactions very much with the help of the structured atom model. And that is one of the avenues, I believe, why the structured atom model would be of importance for the world, right? Therefore simplifies, and it gives specific insights and details about specific nuclear reactions, which you could never do before because we didn't have the resolution of the nucleus.
So can you give an example? Sorry.
Say again?
Could you give an example?
As nickel 62 plus a proton or a hydrogen, where you have a strip of its outer electrons, so ionized hydrogen, proton, that will become a copper 63. Or if you consider another possibility whereby under circumstances You could get a oxygen in a you can create a silicon, or the more classical example is two deuterons together, two heavy hydrogen, creating a helium. So there.
Yeah, I've cut to audio, so if you get cut the picture out, see if we can get better audio.
Say again, please.
I said I cut the cameras off to see if we can get better audio.
Right. You're still saying poor network.
Yeah, no, it is. They've really, yeah. Thanks. Anyway, carry on. Sorry, Ed. Carry on.
Yeah, where were we?
What we got?
Transmutation.
Oh, transmutation of elements going up or down.
Well, yes, it can go down too. Electricity, I think Tesla mentioned something to the effect, take it for what it's worth, that to his satisfaction he electrocuted elements, if you will, and disintegrated them basically, and satisfied himself there was no energy hiding there in the nucleus. But loosely quoting Tesla here. Fission is of course the breaking down, and this is of course something that we see. And yeah, we need to keep that in the back of our minds when we do experimentations. Also called fusion or Langer experimentations. As long as we don't control the environment and the things that are happening entirely, we need to cause by accident fusion or fission processes occurring. And there are stories in the cold fusion field, if I may say so, about being hauled in the floor with a few hundred watts in an experimental setup. So you're talking a few light bulbs here, right, which should not cause a hole in a concrete floor, for example. Loosely. So we know these cold fusion, these Langer reactions, they do take place. There are nuclear reactions happening, more or less chemically or electrically induced, but we still don't know exactly how it works. That's why it's not acknowledged and it's not accepted.
No. But hopefully experimentation will change that. You know, if we can get the funding.
Well,
I mean, could you come up with an experiment?
Let me respond to that. There are plenty of experiments already out there that beyond a shadow of a doubt show transmutation.
Right.
So that's happening. We cannot predict it, we cannot control it, and we don't understand it. And the don't understanding part is crucial here. No theoretical physics model, if you will. Is there any of this? So meaning if you look at the current physics and chemistry out there, the conclusion is this cannot happen.
Yes.
And of course that's what the mainstream components would argue. And they have a point there. The thing is, we simply don't have a theoretical model that explains this, and that is what currently the whole field is trying to work on. So actually, I would argue in response there, Philip, that the experiments are still very important, mind you. They need to be done. We need to attract more money because there's hardly any money.
Yeah.
But theoretical component is crucial here. So even if you're going to do an experimental setup that shows excess heat, that shows transmutations, you still can't really get it accepted because we don't know how, we don't know what's happening, let alone that we can control.
Isn't that a bit perverse though? Because surely theory should follow evidence. So there's all this evidence that you've mentioned about transmutation, and people are saying, "Oh, that can't be happening because we haven't got a theoretical model that fits it." Well, every other theoretical model that's ever sort of been developed has been developed to fit facts, hasn't it?
Well, I think you're definitely partly right there, but what I'm referring to is, look, if you don't even know what the structure of the nucleus is, of a particular element, let alone an isotope, can you discern what is actually going on there when it changes into a little bit of a different structure of a different element? As long as we don't understand that and do not even have that accepted in any way, shape or form, so you can totally ignore the structured atom model that I'm working on, it must be true. Otherwise you cannot have this. And as long as we don't know that, how are you going to reach the theoretical model, of course based on observations and all that, right, are extremely important right now.
So, well, I still go back to the ether being some way involved with it, which is obviously largely ignored. I mean, how do you come up with an experiment to actually see if it is the ether interacting with the nucleus that creates all these variants we see?
That means there's a constant from that. And how are we going to discern? It's horribly difficult problem.
Yeah, well, as far as a constant, then we have to go back to the hydrogen, don't we? 1 and 1.
Yeah.
I think so. I would have thought so. Because that's, once you get above that, you're confusing stuff. But if you're going 1 proton, 1 electron, whatever that electron is, and you have to start from that basis, I would have thought.
A neutrino is, or an antineutrino, I should say, comes into existence in quantum mechanics through the reaction of a free neutron.
Okay.
Free neutron. Decaying into a proton. As I put out a pair. Plus.
Sorry, can you say that again? We lost you on the line.
Therefore, okay. A neutron decays into a proton-electron pair.
Okay.
An antineutrino. And the antineutrino is scalar spin number. So we have a neutron with a spin of a number of an electron, and they both have a spin number of plus and half. So that doesn't work, right? Excuse me, the neutron also has a.
This is totally breaking up, Eddie. We can't hear a word you're saying. The line is absolute rubbish.
It is.
Yeah, no, we didn't hear hardly any of that at all. So we're going to persevere, but obviously, we're getting very, very limited bandwidth tonight. Hello?
Excellent. Again, if I come through, am I coming through?
Oh, you are. Yeah, you are now.
Okay. So everybody can look it up, Philip, to complete this. A neutron decays into a proton electron, and they all have a spin number of a half.
Right.
So half is half plus and half. Of course, that is not a correct formula, right? That doesn't add up. So what they did is added minus a half, and that is your antineutrino.
Why do you need that? Why do you need this antineutrino?
Otherwise, you get half plus and half equals and half. That's not true. Half and a half equals 1.
There's something wrong. I can't see how, just to make the maths fit, you invent an anti-neutrino. The maths has got to be wrong.
Well, the moment you accept the antineutrino, something else may go a little bit wrong. And that's kind of where we are still. We still try and fix it and find the proper way. But there are many arguments to be made why this is not the proper way of doing it. Now, I'm not saying a neutrino, or what we call a neutrino, is not a real thing. I don't know. But it could be something else, or misinterpreted, or, there are many things that could be happening here. It's a difficult topic.
Well, it's good there's still some stuff in science left to be investigated.
Oh, there's plenty to be investigated. I promise. Yes.
So, in your model, the neutrino is actually a pair, is it, of a proton and
Electron.
an electron. Is that correct?
I don't actually, I consider a neutrino almost, and forgive me for people that would be offended, but of no consequences for the model. Kind of like we have no strong force because it doesn't equate in anywhere, there's no need.
So, for example,
We're dealing with electron.
how do you account for the mass difference between hydrogen and helium then? For example, I mean, I know that's why the neutrino was suggested. I was going to say invented, but because the mass difference between hydrogen and helium is, I think, a factor of 4, and by itself the proton didn't provide enough mass.
That is, well, ongoing topic of research. I cannot give you an answer in that sense.
Sure.
What I can see is that it is related to the structural component as well, because what we're talking about here is binding energy, and of course that is totally related to what we call a mass defect there. I cannot give you a definite answer there. I'm not a physicist in that sense, right, into these hardcore things, even though it's an important topic for me. We are trying to focus on the connections to the structure of the nucleus and the elements, right?
Yeah.
And work together with people that are more versed in these topics. People like Eugene Bagashov, for example.
For sure.
So we're trying to work with him, and that's just an example, and some other people in the cold fusion field, so the ICCF. There are some people there that we sort of create an atomic research group. So these questions are very spot on. I just cannot always give you an answer yet.
No, that's fine. We're just exploring it and trying to answer questions which other people will ask. So we're just exploring.
So we're trying to be basic, and we could go into the topic much more, but that more specifically dealing with the binding energy, missing mass defect, etc.
Yeah, I like because when I was, obviously we got your video up from last summer, and I was watching it again today, because obviously, and because obviously, like I said, it's not really my field at all, and I like the idea of exchanging different. When you're getting molecules, you've got different atoms of different amounts of charge, literally binding or not binding, and then it does seem like an exchange of charge. Almost that does, to actually make the whole molecule work is something. Yeah, I'm trying to get my head round, really.
So, can you put that in a question?
I don't know. It is. But the thing is, when I look at pictures of molecules, you quite often have one line between two bits, between two hexagons, and sometimes you get two lines. Do you know what I mean? When you get a picture of a molecule?
A molecule or an atom?
Hold on, let me get a picture. Let's take you down a bit. It's probably audio is probably going to get worse because I'm opening up a browser. Yes, and we'll just get in.
So I'm not sure if you're referring to a chemical connection like a single or double.
Yes.
Yeah.
Okay. You'll be your valence number or your oxidation state.
Yeah, this sort of thing. Yeah. You said, but some of them have one line and some have two lines. Can you explain what all that means? How because we're obviously trying to explore this stuff, and obviously not many people are well versed in it. So can you explain how that works?
Sure, chemistry 101, if you will. Right?
Yeah, absolutely.
We take an oxygen and we say, and this is something that we deduced, for example, through early explorers like Dalton.
Okay.
An oxygen, we say, has a value of -2. That means it can make two connections, and it tends to be negative, meaning it wants the electron. That's in chemistry.
Right.
So here come along two, or an H2 comes along, right? And hydrogen gas comes along. And it's being ripped apart in two parts, an H and an H. And each H causes oxygen, but the oxygen can make two connections. So what you get is two H's and one O. And they're both singular bonds, if you will. One bond between the hydrogen. Another bond between another hydrogen and the same oxygen. If you look at a CO2, for example, a carbon has a value of 4, in this case a plus 4, and the oxygen still the minus 2. So you need 2. So plus 4 in total, and 2 times minus 2. And that is a double bond. And the single and the double bond can also exist between carbons in a chain or in a hexagon in chemistry. So the most simple sugar is in a hexagonal shape, and almost every point is always a carbon.
Okay.
Usually there's one is an oxygen or a nitrogen and something to that effect. You can look that up on Wiki if you're interested, sugar. But so then you can add biochemistry here can work with single, double, and even triple. So it totally depends on how many connections it makes. That's your bond.
Okay.
And how many connections, of course, depending on the element.
Well,
And to make the connection to the structured animal there is. In chemistry, we learn, of course, that this is the field of the outer electrons, right?
yeah.
Which are shared between those. So it's sharing 1 or 2 electrons. In the structured animal, we find those outer electron properties, these valence numbers, come straightly from the nucleus. So that's another part of why the structured animal is important. It connects physics and chemistry intimately. Directly into the other, if you will. Physics goes directly into chemistry. There's no more dividing line there.
Okay. So.
Hope that helps.
Sorry? Breaking up as always. Well, look, you got any other questions or? I mean, obviously, we was hoping Piers was going to be here. Yes.
Piers said he's on his way. Do you have any insight, Ed, as to the difference in? I mean, actually, I think I was going to ask you about the masses of protons and electrons, but it seemed to me you were saying that you felt that the nucleus was, let's say, solid, and the electron was more the electron cloud. You don't perceive the electron as a particle. Is that roughly correct?
Yes, although there are attributes to it that makes it more like a particle, right? But we don't know exactly. We don't know what an electron is still.
No, yeah.
Without.
Yeah.
But yeah, more like a diffuse thing, not like a particle, spherical, hard-shelled thing or something. No.
Sure. And in that case, how do you see the electron in whatever form interacting with the proton and therefore making the structured atom equivalent of a neutron? How does that interaction take place in your mind's eye? I know you can't define it, but I'm just interested in trying to understand how you picture it.
Well, wow, this is fundamental. We start off in the structured atom model by describing the following, and this is from the top of mind. We have a duality, which we call proton-electron pair. And of course they are like opposite, right? But they are attracting each other, so that's why I say I kind of see conceptually the proton as the carrier of the charge, the electron. I don't know why they attract. I don't know what it is that makes it do things. All I know is of course they are do not annihilate. Coming back to one of the previous questions.
Yeah.
But why that is, I cannot answer you. I think that's a creational aspect that's above my pay grade. Yeah. Sorry to disappoint you there, but that's really where I draw the line or the limit.
Sure, I mean, you've obviously given this a good deal of thought. I'm still just trying to tease out, if you like, the fundamentals of if you like, your mental building blocks that you put together to create this model.
So there's something that might help. So just imagine for a moment the electron being a large sphere, whatever, fuse, right? Not half shell.
Okay.
And so the negative charge would attract both protons to that sector of charge. Now, if I have a tetrahedron, so 4 spheres,
yes,
still have an electron in its center, and all 4 would be attracted to its shared combined center, if you will.
So those 4 protons wouldn't be repelled because of the attractive force of the electron. The one electron stronger than the 4 protons.
Well, the average ratio is 1:2, meaning 1 electron holding together 2 protons.
Right.
Ratio that the elements have. Right. So 1:4 would be a highly stable nucleus. Actually, it would be a 1 neutron. That would be 1 neutron and 3 protons. That would be a lithium-4. So that it wouldn't like it. It would either totally immediately start electron capture, which is very likely, or explode into pieces.
We're dealing with large-scale magnetic fields and related phenomena. But of course, the way things work at a detailed level probably does affect the weather. But we can't, there's nothing I'll do about atoms, which is different from normal physics at this point in time.
Okay. So yeah, it's still going back to what interests me with the weather, especially, is the fact that the change of matter states. You know, the way I describe a lot of wind is obviously the H2O molecule going from the gas state into the water state, and so it loses energy. Yeah, I mean, how do we make a decent cloud chamber? Because cloud chambers are basically alcohol. You know, it's misted alcohol.
Well, they can do anything.
And I mean, does that make any difference? The fact it's alcohol rather than H2O. You know, does that nullify the result in your opinion or not?
No. I mean, it's just you have a vapor that's supersaturated.
Okay.
Put a charged particle through it, and it will cause nucleation and lose a track. Right. And this has been going for, since the 50s, I think these things were developed, so they're not new at all.
No, they're not. How relevant they were in reality.
Well, they're for measuring tracks, and then they were converted into the bubble chamber, so we put things into liquid hydrogen or something, and then you get a track of bubbles. And recently CERN has done some more experiments kind of confirming that these things happen. But they've been announcing this as if it's something new, when it is completely ridiculous. It's not new at all. The bubble chamber is at least 50, 60 years old.
Okay.
But you see, Mishler, the guys in who believe in galactic cosmic rays are getting CERN to test this stuff. And then therefore saying, oh yes, galactic cosmic rays change the weather, but that is complete poppycock. All they've done is tested something in a cloud chamber. I don't know if this is relevant to what you were having on.
Well, I mean, we're just talking generally because like these next few months we're trying to work out the curriculum for our summer school, and so we are just exploring the different scales from the nuclear up to galaxies and beyond, has been subset by Rob.
Okay.
And we're now exploring how we're going to. Well, again, exploring generally Edwin's model.
Okay. No, I think we should look at all scales.
But it is seeing how we can actually incorporate this into our curriculum. Which will be coming.
Okay.
So
Well,
it's just a general discussion.
If you're going to talk about the weather, the issue of galactic cosmic rays is important, because the Svensmark theory is that it's cosmic rays which are the means, the means by which the sun and the earth are connected.
Okay.
Now, this is complete nonsense.
Constant
Complete
rays.
nonsense.
That connects by Bergen currents.
Well, what his argument is that
Okay.
the sun's magnetic field lets in cosmic rays when it's weaker, so there's more cosmic rays
More coming in.
here,
Okay.
and those cause cloud nucleation,
Yeah.
which is
yeah.
fine as a theory. But
Yeah,
you see,
so
what it would
that
mean
people say that. Yeah.
is that the periodicity of world temperatures is going to have to be the same as the periodicity in these modulated cosmic rays, which
Yeah.
will be 11 years.
Okay.
However, that is not observed. What you have is the main signal in the Earth's weather is 22 years,
Okay.
which is the magnetic connection between the Sun and the Earth, and therefore the particles from the Sun doing that. And when you look at the figures, it's completely obvious,
Yeah.
because there's 300 times more energy in solar particles than there is in galaxies, even though they're higher energy, but they slow down to interact. So basically, the Svensmark theory is 99.7% nonsense. However, they carry on propagating it by smudging the data and not actually comparing things over 5, 10 or 11 years, but smudging all out over 22 years or 30 years, and then of course you get something that it doesn't show what they claim it shows. And of course the global warmers love this stuff because they can point at the Svensmark theory and say that is the solar theory, and then in 2 lines they can say, look, it's nonsense, and therefore if it's not a dog it must be a cat. So if it's not the solar theory, it's carbon dioxide. So that's why CERN wasted huge amounts of money testing irrelevancy, which
Well,
is already.
isn't CERN a huge waste amount of money?
Well,
stop.
Maybe,
do you see
I
any?
wouldn't
Do you
say
see
that,
any
but-
relevance in CERN and what they do here? Really, Edu?
Thing that I can, with all due respect towards CERN, because I do believe they're doing something there. I mean, even these people wouldn't waste billions a year.
You're right. There's great stuff going on there. I mean, but
Well, to my mind, what they're doing, what it's called sometimes, is an atom smasher.
Yeah.
And one of the things that I could envision is that they're still trying to, by smashing the lead atoms together, breaking it in all the little pieces, and measuring them in these huge detectors, and then kind of winding back the clock of that explosion, figuring out what the pieces are and how they fit together, figuring out, one of the things they would be figuring out is atomic structure in my mind, and of course, figuring out when and where you can harness energy and all these things and whatever they have and all kinds of research that they're doing there. I'm not taking into that. But I think figuring out the secrets of the nucleus is high on their agenda somehow.
yeah, well, I think it's great, but it's expensive. But one has to say, if you want to understand how an apple is made, would you do that by firing apples at each other at huge energies?
No, well,
You wouldn't, would you? I mean, so the point about CERN is it's doing things in a certain way. There might be other ways.
Well, is it just making atom debris? It's always been my question. Is it just atom debris, which they call smaller particles? Just because one spins that way, they call it something. One spins that way, they call it something else. Of different flavours. But are they just making atom debris?
Well, if you want to call it atom debris, you can. But I mean,
No, it's either debris or it means something.
Oh, it means something. Yeah.
Does it?
Well, when you cannot simply pluck apart the nucleus of any atom that we know of in any way, shape, or form, so we're only left with smashing the thing, trying to detect the fragments, right? Observe them and do some re-engineering, if you will, and figuring it out. But we have little other means. So
has anything come
So I agree with the notion, myself sometimes try and make it a little bit ridiculous or, make fun of it like atom smasher and breaking them up. But on the other hand, do we have something better, right?
Well, I was going to ask, has anything come out of CERN that's informed your model? I mean, any of these exotic particles, no?
No.
And of course, the Higgs boson hasn't been found, has it?
Well,
No, it hasn't.
Well,
that's why they call it a Higgs signature. If you go into UCL and you go into the Department of Fanciful Thinking, you'll see a poster proudly on the wall saying the Higgs signature. And that's because the word signature, one of the definitions, is something that's agreed upon. It's agreed upon. Yeah. It's only been agreed that it's found. They've never found the Higgs field to have to find in order for it to stand up. I mean, am I being over the top here, or I don't. I don't
think you're looking at these PR department.
When you're looking at these small,
they know what I think.
Yeah, but Philip, they're all very short-lived particles. So the only way you can see them is by a signature. And you can like it or not, but that is the accepted way of identifying particles. You have a signature of a certain energy. However, the idea that the Higgs boson has been found is actually a bit disputed, because last year I was at Imperial College, where there's undergrads doing lots of projects, and they were looking at all the data, and they said, well, it could be this signature, or it could be that one, or it could be whatever. So it's
one
not
they agree
actually.
Whether they agree it's that one, agree that
one. Right. You see, the announcement was a bit kind of premature in that it was making certain assumptions, right?
Okay.
However, of course, if they're now not sure, then there's room for more spending on more.
No, that's right. They didn't find it. More money goes in, make it faster. More. Yeah, I mean, money down the drain or what? It's an underground pipe full of something.
Well, a lot of stuff has come out of there, and there are definite patterns in basic fundamental particles and so forth, which are quite amazing. A bit like the periodic table of the elements. I mean, much smaller scale, obviously, but it is. No, I think it's good. You might argue about spending that money instead of on the National Health Service or something. But
proper science.
Well,
or is that again?
No, it's proper science, but the spin surrounding it might not be proper.
Which spin, that way or that way? What way of spin are we talking about?
Well, I don't know, are we talking too fast? Or are we all right? Can you hear us?
Can you hear us, Edo? Are we coming through okay?
So, yeah, I can follow, but say again, please, the last sentence there.
I said, can you hear us?
Yes.
I had a question about your general theories, unless you want to carry on talking about CERN and the like. Is that, do you accept standard relativity and four vectors and that way of, doing things, or is that like, have you moved beyond that?
I live in it. Well, good question, Piers. Thank you for that. I would argue that I already live in another paradigm.
Okay.
So you could call me crazy for that, of course.
But
right?
four vectors work, don't they?
The thing is, you said relativity.
Yes.
I don't do relativity at all. Basically, I consider I don't see where it even enters the equation, where it enters the need for anything to understand anything. I don't think relativity is good at all.
Okay.
Quantum mechanics is far better, although there are some things that I tend to point out or fight with or struggle with, but that's...
Well, yes, don't we all, yes.
Yeah, but relativity, no,
I'm talking about special relativity, E is mc squared and the concept of four vectors and so forth.
Everybody can, this is a bit off topic from structured animals.
Yes. Okay.
If you look at the idea of time travel, right, and everybody can do this little mental game, mind game themselves.
Okay.
So you have an observer and a traveler.
Yeah.
The observer is on the Earth.
Yeah.
The traveler is going to travel 1 light year with the speed of light in a certain direction, and let's say he reaches whatever it is, Alpha Centauri.
Yeah, that's what they always go in the textbooks. Yes.
It's further than that, but let's just say it's 1 light year. So the moment the traveler starts traveling with the speed of light, the light that receives the observer that stays at home, so the speed forward is the same as the speed backwards.
That's what they say, yeah.
So that's your freezing effect, if you will, right?
Yes.
So, but if the traveler reaches the destination after 1 year, what happened in time perspective? So Mr. Einstein, I don't agree with him at all, and everybody can validate this and verify this on their own. The traveler has had 1 year of passing time.
On his clock,
And
on
the
his body.
observer,
Yeah.
and the observer has had 1 year of passing time,
Yes.
except when we start cheating. This is where Einstein, he started cheating.
Yeah, yeah.
What he did was this. The observer, left on Earth, looks at the watch of the traveler, that's cheating,
Yes, it is.
that's cheating, and says, oh, hang on, the time looks to be standing still because of that speed forward and backwards. If you will,
Right. Okay.
So all Einstein did was cheating by looking at somebody else's watch that's way off.
Must have been a consultant.
So, and then the reverse is true too. Suddenly the traveler is there in a flash of an eye, in an instant, and all the information comes back instantly. So what you do in the end is like an old movie theater film roll, the big
Yeah.
rolls. So what you do is instead of playing the movie at normal speed, normal time perception, the first part you do like really, really slow, and then the rest of the movie, when you return, it gets played off all at the same moment. The rest of the movie gets played off at the same moment, and that's a flash of light. So even the idea how this time travel is explained in movies and relativity and Mr. Einstein, it's not even correct according to their own rules, and they cheat. So I don't do relativity at all.
Okay, all right. He's gone.
No, so if you're still there, you're still, don't worry, I've just got to check the line. Carry on.
Yeah, all right. Okay, I'd have to think about that argument, but I mean, I see where you're coming from. Now, however, the idea of time dilation, as it's called, is used to explain why pi mesons reach the surface of the Earth rather than decaying on the way. Now, they use this time dilation, which you're arguing with, but they use that to justify pi mesons reaching the Earth. Now, what's your take on that?
I really don't know, Pierre. I couldn't answer that decently.
Okay. But see, that's one of their tests, right? So-called. Physics 1, that's a test. They say, yeah, okay, pi mesons are here. Einstein's right.
Can I ask?
Well, but
Piers,
I agree there's many hurdles to
Can I ask just for, obviously not me, but for other people, what pi meson is?
Oh,
I was joking, I don't know what it is. So.
no, well, okay, well, pi meson, no, I'm not I'm laughing because it's a particle, but the point is that it comes from collisions. Right. It's a bit of the debris which Philip talks about, but it has a short life. You see, when you make them in the laboratory, they've got a short life, so they couldn't still be here. Yeah. They couldn't reach the Earth in the time it takes to reach the Earth from the upper atmosphere because they would have decayed. However, they do turn up. So time dilation is used to argue that their life relative to the observer on the ground is extended. You see, by looking at their watch, by a trick, as whatever. However, the trick does seem to work. I know because the pi mesons turn up. Now, that is what it says in standard textbooks. Now, of course, there's all sorts of things. Did the pi mesons really come from the top of the atmosphere, or actually were made lower down? There's all sorts of stuff. But that is the argument put as evidence.
That's the only one they got. Which is fudging, because it could be anywhere. I mean, who says that does come from up there?
Well, they've got good arguments about where these, because there's going to be high energy cosmic rays, where they're going to start hitting stuff, because it's where the atmosphere starts getting denser. So there's a case there.
So It's not possible for me to make any decent reply there to your specific question, Piers. But what I can say is that when you, for example, we touched upon the neutrino, and the neutrino entered the equation literally by putting it there because it went wrong.
It was to conserve momentum.
Yeah,
That's
exactly.
a great idea. And I've done loads of work on neutrinos, so they're fun to do, but they may be delusional.
Well, I didn't know you worked on neutrinos.
When we accept that neutrino in that place and start working with it in a specific model that we are creating, now it becomes a real thing in my model and a real issue and maybe even a real problem, and maybe I can use it rightfully or wrongly, doesn't matter.
Yeah.
If you use time dilation from a specific model, which is the relativity, general relativity, special relativity, whatever, the relativity part, and you start working with that because that is what your model does, then you can work with it and talk about it.
Yeah.
What I can say is, and that's kind of what I'm trying to say, is it really is not part of the equation for me in doing anything with a structured atom model or looking at an electromagnetic nucleus or something to that effect. So what I'm saying is, so far, at least on my path, relativity in that sense didn't enter the equation except to what I just told you about.
Okay, that's fine.
I got someone asked Laplace if he believed in God, and he said something along the lines of, "I've never had need of that hypothesis." It sounds to me like, in terms of your structured atom model, you don't have no need of the relativity hypothesis.
Well, didn't he also say you better play safe and believe in God?
Oh, I don't know.
Because you see,
I'm selectively quoting.
if God exists and you believe in him, then he'll be all right with you. But
Okay.
if you don't believe, then you go to limbo.
That's good advice.
Yeah.
I wasted my Sunday afternoon.
You did. You should be in church.
Should be in church. Can I ask, going back to what you were saying earlier about how the structured atom helps tie in physics with chemistry? Again,
Tell us more. Yeah.
Yeah. Well, I'm aware of how the Bohr shells, if you like. You have the 2 and then the 8 and the 18. Talking about obviously the electron shells. Can you speak again about how the structured nucleus that you're talking about relates to the familiar sort of periodic table? Because that's, I think, a real payoff of what you're doing.
Okay. There are some pages on our website that deal with this topic for anybody interested to take a good look there, right? It's a little bit difficult.
We should do that.
Well, we got your website up here, Ed.
There's a little picture there. That's fantastic.
So do you want to talk us through this?
Well, we can do that, but
or give a bit. Anyone who goes to your website, they're obviously going to be landed with this. And if they're new, what can they look at? Obviously, you got all the atoms down the right hand side there. I've pulled out, I think, oxygen.
What you're seeing here is the viewer, so you can take a look at the specific elements and some isotopes there. Mm-hmm. But in this case, I would like you to go to on top of the page. It says structured atom model, the second one.
Yeah.
Yeah. You can go there, please.
Yeah. Well. Yeah. This takes. There we go.
Sure.
Okay.
And then we go to the theory. On the left, you see a menu, and it says the SAM theory. If you can hit that one, please.
Okay.
And then one more. I would like you to go to. Give me 1 second. I need to check it if it's the right one. If you can go to the cycle of 8 there, please.
Cycle of 8.
Up one.
Cycle of
No,
8.
down.
There you go, yeah. Oh, so I can. Okay, cycle of 8.
Okay. And if you slowly scroll down a little bit, I know I'm testing our connection there.
Yeah, you are. There we go. I think they heard us and I put the bandwidth up because it's working properly.
It does seem to pop up less this.
Well, they don't want bad publicity, do they, really?
You're hitting the pictures now, so. So
I
scroll
don't
down.
know.
Scroll down.
Where do you want to get to?
A little bit downwards. Yeah.
Ah, there's a picture.
Okay, please. So what you can see here is this cycle of 8 thing, and there are a few more pages there that everybody can look up themselves.
Okay.
What you basically see here is 2 cycles of 8 in comparison. So the 2 first rows of the periodic table,
Right.
except
Amazing.
you can up to that one.
Yeah.
Oh, there's one lacking there. How about that?
Lithium, yeah, you're missing a picture.
Lithium, well, it might be, you mean it's disappeared because of the bandwidth, or it's...
Got to check your website.
Yeah, it could be a little bit.
Someone's stolen it and run it out.
But it should have only the red part there, only red, and which you see on the right there with the magnesium, for example, it has 2 of those, the sodium has 1. Now what I'm saying is there's a periodicity of 8, and it starts at the lithium. And and there's some extra text there. Now here's what happens. The lithium is at +1. Then you go to beryllium, below that it's a +2.
Yeah.
And below that you get the boron, +3.
Yeah.
Below that, the blue is the carbon, it's +4 or -4. The CH4 gas, it's -4. Then when we continue, we get the second part. And that's the nitrogen, -3. Oxygen, -2. Fluorine, below that is -1. And then below that is 0, which is the noble gas.
So hang on. So all the noble elements, factors of 8. Is that what you're saying?
They're always like with these green endings, so no colorful nucleates no more.
Yeah.
And this is the most complete shape. Now on the right column, you see the same thing, but a periodicity lower, right? A row lower.
Yeah.
The same column or cycle of 8.
Yeah.
Now this cycle of 8 is what keeps returning. So you see that the lithium, when we start with the red, it ends up with a neon. But in the larger elements, in the bigger, much bigger elements, you see nothing but these neons, if you will, combined.
All right.
So what you get is +4, +1, +2, +3, +4. Switch -4, -3, -2, -1, 0, and then it repeats. And every time the structure starts to grow again with a lithium, the red part, and way on top you can see the first one, if you scroll on the top picture. You can see from the neon, of course, this is the next one after neon, and then the next red piece starts to occur. Only now you get, at a certain point, you get a combination of multiple growing spots. So several cycles of 8 start to conflict, or rather grow in between each other. That's why the period becomes longer in the periodic table. So you get these longer rows that you can see. So the whole nucleus is nothing but a continuation of this cycle of 8, this principle of a growing little group. The red one grows into the blue, the carbon, which is in the center, and then it ends up with the neutral state, and then it repeats. That is what the nucleus keeps doing. And all the properties that have been attributed to these specific colorful groupings, these nucleates as we call them. So lithium is always a +1, and you can see 2 pluses, and magnesium makes it 2+, etc., etc. And that is the logic in a nutshell, and then you get the whole periodic table from that.
Makes sense to you? Yes?
Yeah. So when you've got these pictures, this is those haven't been, well, they can't be measured, but you're pointing out that things will fit together if these pictures of compacting of spheres is used as a model. That's basically what you're doing, isn't it?
Well, if you can go, Philip, one more thing back to that atom viewer. It should be on top of the left, on the left there in yellow. Explore the elements.
Atom viewer, draw the elements.
Yeah, explore the elements. That's we call that atom viewer. So if you take a larger element like, what's the lowest one there?
Iron.
Well, go there, please. So here you see a larger element, and I forgot where I was going with that, but here you can see how it combines and keeps growing into a fractal, if you will, a tree-like structure.
Yeah, well, it's remarkable, isn't it?
So, iron has these particular properties. How do you see those?
On the left, you see the properties. That was what I was going to say. There are some properties there that we entered into it, so you can check those numbers and those values, etc. And you can go to the Wikipedia pages or physics books or whatever, and you will see this is a truthful. These are taken from the whole body of science.
So how do you see these? For example, the properties of iron being represented by that depiction. How does that depiction help us understand iron better?
Right. Well, first of all, it's meant to, of course, it's more or less a teaching tool in my mind. What you can see by looking at this structure here, once you are familiar with it a little bit. So imagine you've had, your classes for a year in chemistry and physics. By then you can totally do this very easily. We can take a look at any atom, we can identify it. We see two green parts there. Those are the neutralized parts, so they are like the neon and the argon, noble.
Yeah.
So the left part here, the green part, that's like neutralized. It doesn't do anything.
Sure.
Yeah.
Neutral, like a shield. The red, we always know the red one is always a +1. And we have two of those, so I can read instantly the valence value here. Oh, it's a +2.
Yeah.
Okay, because in those clusters of red particles, well, there's 6 of them.
Yeah, 6 spheres. Yeah.
6 spheres, and because they're missing, you're two particles away from a stable. Is that right? You're 2 particles away from stability there. Is that what you're?
Well, what it is, the red part, that's why we made it red, simply means I'm red here, I have a valence of +1, if you will.
Oh, okay.
Yeah.
So you've got both of them.
Just by looking at it, I can instantly see, just by looking at the color and the number of those colors, I already understand what the valence is.
Thank you. So why does it have a valence of 1 if it's 6 particles and 8 makes for noble stability? Why is 6? Why isn't it 2?
Well, that goes in way much deeper into the details, but what you get is a plus and a minus in chemistry is not, we shouldn't really use that term yet. It is handy. Why it is handy is because when we put things into solution, like an HCl, which is chlorine acid, right? It breaks up. So the proton, not the electron of the H, goes to an H3O plus. So it's only the proton that went to one H2O. And the electron kind of sticks to the chlorine still, Cl minus, right?
Right.
So this is why you call the chlorine the minus part, because it wants to keep a hold of that electron. So that's your minus and your plus.
Yeah.
But it's simply a connection both ways. That's more truthful. However, we say the electron is connected more towards one side, depending on the electronegativity. So lithium, the red colorful part, or the yellow and the blue and the orange, that is a lithium, beryllium, boron, carbon, they are the metal-like parts, and they are the positive parts. But they tend to have more neutrons or more electrons inside their structure, in the nuclear structure, which is what we're looking at. So it tends to be able to release a charge, an electron, quite readily. It can more or less easily miss one in the combination, but the chlorine, in this particular case, is almost complete. It is almost that noble gaseous state. And so it really wants to adopt that state. So it wants to keep hold of that electron. Now, behind this whole story, and that's the nitty-gritty of it, and I would opt not to go there right now, really becomes difficult, including for myself, and I call out for help for electro engineers and whatnot, right? But what you can see is, and this
Neil Thompson, where are you?
it's in on the top left. You also see binding energy. I can't really read it, but it should be there. Binding energy, 4 numbers there, 3 numbers and an accuracy on the left.
I was going to ask about that.
There it is, behind that one. So it says binding energy in
I see neutral on actual SAM and accuracy.
Yes.
98.9% accuracy.
Yes. So this is a binding energy thing that has to do with your mass defect, the binding energy of the nucleus, meaning how strong is it to keep that it keeps it together. How much energy do I have to put in to distort it, if you will?
Right.
Now, the thing is, we can do that quite precisely, not entirely yet, it's a work very much, but what we can do is also do that calculus pretty neatly and pretty precisely, and we can understand it. So every state that I just talked about all these positions, even in chemistry, represent, of course, a specific amount of energy, if you will, and that determines, in the end, if you have an exothermic or an endothermic reaction, right? So all these positions, all these spots are always related to the amount of energy of that particular state of that element. So that's why you get your chemistry or nuclear reactions, endothermic, exothermic. We can, with practice and the numbers on the left and some extra other things, we can read that all from this model, if you will, from the structure.
So you're saying that your way of packaging also explains the mass defects, because the mass defect is used in standard physics to say, well, okay, when it's greatest defect, then it'll hang together. But you can make a structure and then work out what the mass defect is going to be. Is that right? I think he's nodding.
It's very, well, kind of.
Okay.
This is an ongoing debate, and it's really difficult for me to even talk about it in that sense, because what is the mass defect?
Yeah. Well, it's a bit of his MC squared stuff again, you see.
Sorry?
Well, it's an amount of mass missing, and they say, well, that's E equals mc squared is the amount of energy. So they're using a bit of special relativity as in the discourse. But you see, your point is that you can make these models and things fit together like naturally without arguing about mass defects or not, which I find it very interesting.
Well, mass defect is because they don't understand that mass changes with the amount of charge, yeah?
No? Well, I don't know, parts on that. But I think the idea of things like fitting together in this sort of common sense way is really, really clever, because you see, in chemistry you have surfaces which, where you can have catalysts will help things stick together. And for example, I've seen the Haber process going on and looking through a quartz window, and I think it's on, I forgot what the material is in there. Palladium? No, it's not palladium, it's something. Anyway, the point is the nitrogen and hydrogen will combine together because the surface they're on puts them at exactly the right distance so that they can join up, you see. And you can look through the window and see this white glow. It's amazing. You can see. It has to be under super high pressure. But it's because of crucial things about distances that these chemistry things will happen. Nitrogen and hydrogen will combine and make you ammonia, you see, under pressure. So his idea really is kind of analogous to that, if these lumps of spheres or groups of spheres can fit together in preferred ways, then they will do. That's what he's saying, you see. And it's,
they'll go to a geometric structure.
Yeah.
Sorry?
They'll go to a geometric structure. It all wants to be geometrical.
Well, this might be completely delusional. It might not be like that at all. But this model does work.
Yeah.
I think the thing about physics is people start believing in the actuality of something.
No, a model is a model. It's an interpretation.
Exactly so. Exactly so. An electric field isn't something you can hold.
No.
but you can feel it.
You can measure it.
Well, yes, but the concepts are just writing on a wall. They're not. These equations are equations. They're not things in themselves. That's what I'm saying.
Yeah.
Well, the two ways I know of expressing it is don't try and eat the menu. You know, don't confuse the food for the representation.
That's a good point.
Well, you know, you don't often see people eating the menu, and the other one is don't mistake the map for the territory.
That's right.
Those are the two
Two
ways I know.
interpretations, you know. So, the map is a 2D.
Oh yeah, it could solve the Brexit problem, couldn't it? But
Oh,
John can give.
Send it to
Here
your
you are,
father.
Theresa May. Here's a map of Britain.
By the way, Edwin, from my point of view, sorry about us being well. Hang on, no, let's not get into that conversation. But can I ask, with your, I have a fascination. Let's
We're
say
not talking about Brexit.
no. I have a
We're doing
fascination.
5 minutes, or about 7.5 minutes.
Sorry for interrupting you. I've got a fascination with spin, and just for me, a thought I had was that if you had a spinning atom, you could then begin to explain using centripetal and centrifugal forces how positive, a basically positive nucleus could and a basically negative electron could maintain some kind of distance from one another. Do you see what I mean? The balance of centrifugal and centripetal forces. I wonder whether spin was something you factored into your model.
Yes, if you take a look at on the left side, you can still still see the properties.
Yeah, absolutely.
There should be a spin number there.
Nuclear spin. Yeah.
And so what we did is we simply took the literature spin number and plugged it in there, right? So
that's 0.
Official number. And if you look at the structure, you will see that every time there's an imbalance or an asymmetric situation, we get a spin number, meaning bigger than 0.
Yeah.
And every time we have a symmetrical situation, the spin number is 0. So what is the part of the nucleus that does this? That is the part that is also related to this chemical thing that we talked about with the colorful nucleates.
Yeah.
That is where there are still charges missing. It's not complete yet. It's not a noble gaseous state yet. Those parts of the nucleus are the parts that interact with this magnetic field, if you will, which would try to rotate in a magnetic moment the nucleus. Right? We're talking the nuclear magnetic moment.
And so so the spin numbers that you've taken from reference books, that was like, if you like, a nice accident for you that when the noble gas forms were there, you got a spin of 0. Was that like a moment of something more than you were expecting?
Oh God, it's one of the examples of many of those unexpected things, because this model keeps growing and growing, and no matter where we went the past few years, the moment you start paying attention, you start trying to understand, okay, what's going on here, just by looking and observing and understanding and putting things into the equation, not making up nothing yet.
Yeah.
You will find all kinds of correlations that are way too good to be true.
That must be very satisfying.
Say again?
That must be very satisfying.
It's very satisfying, and it's because only when those things happen, you know you're on the right track.
Yeah, you need positive feedback from reality.
We're not there yet at all, mind you. But
well, once you make the adjustment, my adjustment, I think it'll take you a lot closer.
That was free advice there.
Am I on the right highway to the capital of the country? And when you see those mileage posts coming by with the right number, you know you're on the right track.
Absolutely, absolutely. But yeah, no protons, only neutrons, and neutrinos. Anyway, that's a side note for people. In the Facebook group earlier in the week, I was talking about making myself a grounding device out of scraps, which I had lying around at home. And basically, this is it. I'll be going into detail exactly what it involves in the group later in the week. But basically, that is a 3-pin plug, but there is only one pin in there. Notice, and that's the earth pin. And the lead actually goes in there, goes through the fuse before actually hitting that. So if there's ever a power surge the other way, it'll obviously break a low ampage fuse in there and not fry my feet. And the other end basically goes to 2 plates, which I'm going to be putting into my shoe when I'm sitting at the computer. And I'll be earthing myself directly to the earth strap, and this is a little. No, I'm not going to do it now. Because it's only shoes and feet off. Shoes and socks off. But I will take some pictures when I get home during the week, and I'll be talking about that. Yeah, doing that. Chi, is there anything you want to add? Any developments at all? Or
not that I can.
Say it. Okay, no problem. Okay, well, we just got a couple of minutes now, so we're just going to be wrapping it up. So is there any last observations you want to make, Edo, or any last questions from us here in Shepherd Bush?
Well, I'll just thank you for your time, and it'd be great to talk to you about this, our ambition to create a roughly scalar curriculum. So we're looking at electromagnetic phenomena across scales with a view to maybe coming up with a 5 or 6, let's say, module course, each module talking about a particular scale, and then being able to look at those.
You're talking about distance scale, not time scale.
Yes,
Okay.
Meters, millimeters,
Atoms to galaxies.
yeah.
Okay.
And in that context, what was your starting point? I guess we're coming to the end. What was your starting point for this? Where was it? You talked a lot about the structure. Was it the Platonic solids you started with?
I started with emptying. It's a good question. Let me say this. If you want to understand something, you first need to clear your mind from all the noise, because it's just influence you don't want.
Yeah,
that's
and
true.
You need focus. So this has been a horrible mental exercise years ago, but there were certain phases there when I understand. Okay, by simply reading more, studying more, it's not helpful because I couldn't understand the fundamentals. Right? We are all struggling with that.
Right.
And so what I said at a certain point to myself, and it was partly fed from all kinds of circumstances in life, I said, you know what? I want to redo it because it's more useful for me and it's probably quicker by totally redoing it all than by adopting erroneous thinking mechanisms or erroneous data. And then years and years later on, you're still on the wrong path, right?
Yeah.
So you can't go there where you want to go. So you have to discard everything, meaning you have to accept I know nothing. And then you take a look at everything again, and you only adopt, of course, which you can for yourself, for your own truth, really see as the truth. So something really simple. So one of the first things that I actually accepted as a piece of truth is again, okay, there's something, don't know what it is, and it's spherical and it has volume. It's not an imaginary small dot. And that's not true. Everything has volume. So these are simple notions. When you start with that, start building that away, you get a different concept. So you need to discard some information sometimes before you can go to a different path and figure out things again, if you will.
And how long has the structured atom model been in your head? I mean, not necessarily with the website, but like, what's the gestation period of this been for you?
I started this process, if you will, and I didn't know anything at that moment, in about 2006, 2007, about 2008, with my thinking. So I started with one sphere, right? That was my starting point. Literally one sphere.
Hydrogen.
Then let's put in another one. What happens? And that's the moment it becomes really complex. So in 2008, I understood a little bit in relation to this spherical densest packing, right? Spherical geometry.
Yeah.
And then I started noticing, hang on, this totally correlates with what we see in the elements and the isotopes. So that's when I got a focus in a research direction, if you will, for the first time. Before that, I was very free floating, studying everything again, thinking about everything again, trying to see if I can adopt it again. And in 2008, I had lithium. In 2010, I knew about carbon, so the icosahedron. That was a big step again.
Sure.
And that took me probably another year or two to figure out how the bigger structure beyond the largest perfect icosahedron, how that works. So it's a continuing journey, and you keep finding things, and it's a growing body of work, and it's still very neatly fits together with a few rules, few simple rules.
Well, that's what the universe likes to do things simply, doesn't it?
There's a question on that. What you're talking about, the origin of it, is a bit like that, the semi-empirical mass formula, which is about, adding in spheres, or something, and then you get this kind of periodical changes in mass because they say, oh, these things fit together, and then something else comes along. But when you do that in physics, it's just regarded as a sort of kind of thing that helps a bit, and then they discard it and don't carry on logically to, its logical conclusion, where you're just saying, well, let's just stick with that and go on and on and on, which is quite interesting. So in a way, what you're doing is from an idea which was around but wasn't pursued adequately. So it's really good you have pursued it.
Yes, sticking to the logic and sticking to the truth. And by the truth, I mean only when you can really grasp it in your mind, understand it, know why it's true, and work with very simple concepts, you can do that.
Yeah, absolutely.
So if you go in too much detail too soon and you start doing nothing but calculations, you will be immersed in that, and you will never do that other thing, the understanding and the logic first, if you will.